Electronic circuit boards form the fundamental infrastructure of modern technology. Computers, smartphones, and industrial control systems all operate through these boards. On their surface, microscopic conductive pathways are precisely engineered. At the most critical connection points of these systems, the element gold is used. Gold provides high electrical conductivity and exceptional resistance to corrosion. While gold exists in nature as solid masses, on electronic boards, it appears as ultra-thin coatings at the micron scale. The origin of gold traces back to nuclear processes within the cores of stars. Neutron-star collisions create environments of extreme energy. In these environments, atomic nuclei merge under intense neutron bombardments. Heavy elements like gold are synthesized through these physical processes. During Earth's formation, these heavy elements became integrated into the planet's structure. Chemically, gold is one of the most stable elements in the periodic table. Its atomic number is 79. The arrangement of electrons in its outer shell minimizes its tendency to react. This low reactivity makes gold resistant to acids and oxidation. This noble characteristic allows gold to provide long-lasting contact points in electronic systems. Other metals which oxidize over time lead to connection failures. Gold-plated surfaces, however, conduct electricity continuously for years. Humanity has used gold in its physical form for thousands of years. In ancient times, it was used as jewelry and as a medium of exchange. The Industrial Revolution, followed by the 20th century, transformed the role of gold. As electronic technologies became smaller, gold began to be used at the microscopic scale. Printed circuit boards are coated with gold. Processor sockets and connector pins rely on the chemical stability of gold. Recovering gold from electronic waste involves a sequence of physical and chemical processes. To understand this recovery process, one must examine atomic-level bonds. On circuit boards, gold is layered over copper or nickel surfaces. The thickness of this coating is typically only a few micrometers. Gold atoms remain bonded together through metallic bonds at the surface. Free electrons move continuously within the crystal structure. Extracting gold from this structure requires both physical and chemical intervention. Individual recovery processes begin with mechanical shredding. Electronic boards are physically broken into small fragments. The goal is to maximize the exposed gold-plated surface area. The shredded boards are then prepared for chemical processing. The next step is dissolving the base metals other than gold. Metals such as copper and zinc are far more reactive than gold. These metals readily dissolve in suitable acidic solutions. During the chemical reaction, electron transfer occurs. Copper atoms lose electrons from their outer orbitals. As a result, they transform into positively charged ions with a +2 charge. These ions disperse into the liquid solution. Gold atoms, however, do not lose electrons in this chemical environment. Gold remains in solid form on the surface. As base metals dissolve, gold flakes begin to detach and become free. The solution is filtered to separate solid gold particles from the liquid. However, these flakes are not yet completely pure. They may still contain microscopic traces of other metal atoms. To fully purify gold, its crystal structure must be broken down. This requires dissolving gold in a different chemical environments. The liquid mixture capable of dissolving gold is a precise combination of nitric acid and hydrochloric acid. This mixture is known as aqua regia. Individually, these acids cannot break down the crystal structure of gold, but when combined, a perfectly coordinated chemical mechanism activates at the atomic level. Nitric acid acts as a powerful oxidizing agent. It begins stripping microscopic amounts of electrons from the gold surface. Gold atoms that lose electrons transform into positively charged ions with a +3 charge. At this stage, hydrochloric acid comes into play. It supplies a high concentration of chloride ions into the solution. These chloride ions surround the freed gold ions. 4 chloride ions bond with a single gold ion, forming a new complex structure. This structure is known as the tetrachloroaurate complex. The formation of this complex continuously drives the chemical equilibrium toward further gold dissolution. Solid gold atoms begin dispersing into the liquid in ionic form. The visible gold flakes gradually disappear. What remains is a dense liquid with yellow and orange tones, containing dissolved gold species. This liquid contains not only gold, but also organic and inorganic residues from the solution. Materials such as plastic particles and fiberglass remain undissolved. The solution is transferred into industrial filtration systems. Under high pressure, the liquid is passed through micron-scale filters. Solid waste is retained, while the purified solution carrying gold ions is collected. The next step is to convert the dissolved gold back into solid metal. This process is known in chemistry as a reduction reaction. Specialized chemicals such as sodium metabisulfite are introduced into the solution. These substances release free electrons into the system during the reaction. The gold ions in the solution rapidly capture these electrons. The +3 charged ions gain electrons and transform into neutral atoms. These neutral gold atoms are released within the solution. The atoms begin clustering together to form microscopic aggregates. These clusters grow heavier and start sinking to the bottom of the liquid. The settled material is not bright yellow, but appears as a brown, muddy powder. This brown powder consists of approximately 99% pure gold. While this process can be performed in glassware at small scale, industrial systems operate within massive reactors. In tanks holding thousands of liters, chemical equilibrium is monitored hundreds of times per second by sensors. Temperature, pressure, and reagent concentrations are controlled by computerized systems. The gold concentration in electronic waste is significantly higher than in natural ore. 1 ton of modern smartphone circuit boards contains approximately 300 grams of gold. In traditional mining, 1 ton of rock yields only a few grams of gold. This makes electronic waste facilities equivalent to above-ground mines. In factories, tons of discarded circuit boards are transported on conveyor belts to autonomous systems. Laser sorting systems optically identify valuable components on the surface. Robotic arms precisely select and separate gold-bearing parts. The selected materials are ground into fine powder using industrial shredders. The smaller the particle size, the faster the dissolution rate during chemical processing. Large-scale facilities do not release toxic gases generated during reactions. Closed-loop scrubber towers neutralize these gases. The acidic wastewater is treated and returned back into the system. This closed-loop system ensures maximum metal recovery without harming the environment. The brown gold powder obtained in industrial facilities is transferred to drying furnaces. High temperatures are required to transform the chemical structure of gold powder into its physical, metallic, and lustrous form. The dried gold powder is still not completely pure. It contains microscopic traces of other metal oxides and environmental impurities. To transform this powder into a pure, solid metal, thermal processing begins. The melting point of gold is exactly 1064 degrees Celsius. To reach this extreme temperature, oxyacetylene flames or industrial induction coils are used. Heat energy penetrates through the ceramic vessel and reaches the gold atoms. The kinetic energy of the heated gold atoms increases rapidly. The atoms begin to vibrate violently within their lattice structure. Increasing thermal energy strains the metallic bonds holding the atoms together. Once a critical threshold is exceeded, the solid crystal structure collapses. The bonds loosen, and the atoms begin to move freely, sliding past one another. At this point, gold transitions from a solid phase to a liquid phase. Liquid gold has a mirror-like, highly reflective and luminous surface. However, a black, glassy layer begins to form on the surface of the melt pool. This surface layer is the oxidized form of the remaining contaminants inside. To chemically separate this slag from the gold, borax powder is added to the liquid. Borax liquefies under high heat and acts as a flux. Liquid borax molecules capture all non-metallic oxides and trap them within. Pure gold, with its high density, sinks to the very bottom of the crucible. The lighter borax slag holding the contaminants continues to float on top. The processed liquid metal is carefully poured into graphite molds with controlled movements. Graphite is a carbon-based material capable of withstanding thermal shocks of thousands of degrees. As the liquid gold flows into the mold, it rapidly loses heat upon contact with air. The loss of heat immediately reduces the kinetic energy of the atoms. Free-moving gold atoms approach each other and re-establish metallic bonds. Within seconds, the disordered liquid structure transforms into an ordered crystal lattice. Gold solidifies again, taking the shape of the mold. The cooled ingot is inverted and removed from the mold. Residual borax remaining on the surface after casting is removed in a mild acid bath. At this stage, the ingot reaches a purity of 99.9%. This level meets the standard of 24-karat gold. However, for aerospace, space, and semiconductor industries, this level of purity is not sufficient. For gold used in industrial electronics, an electrochemical refining process begins. This process is a final filtration at the atomic level. The cast gold ingots are suspended as positively charged anodes in an electrolysis tank. Pre-prepared ultra-pure thin gold plates are used as negatively charged cathodes. The tank is filled with an acidic solution based on chlorides with high conductivity. A strong and continuous direct current is applied to the system. Under the force of the electric current, gold atoms in the anode release their electrons into the system. The atoms that lose electrons enter the acidic solution as positively charged ions with a +3 charge. The anode ingot visibly begins to dissolve and mix into the liquid. Gold ions follow the electrical field within the tank. They migrate through the liquid toward the negatively charged cathode plate. Each ion reaching the cathode gains 3 electrons from the system and becomes a neutral atom. The neutralized gold atoms align on the surface of the plate with geometric perfection. Metals such as platinum, silver, and palladium within the anode remain suspended in the liquid solution. The gold accumulating on the cathode contains no foreign atoms at the microscopic level. Once the electrolysis process is complete, the cathode plate transforms into a dense mass of pure gold. With this method, gold purity reaches a level of 99.999%. This level of purity achieved by gold is essential for the most sensitive manufacturing processes of modern technology. The level of purity reached by gold is essential for the most sensitive manufacturing processes of modern technology. The radiation shields of orbital satellites are coated with gold at this level of purity to withstand the harsh effects of space. The micro-connections inside deep space probes endure extreme temperature variations thanks to gold. Medical implants and pacemakers rely on the biocompatibility and corrosion resistance of gold. Biological sensors implanted in the human body transmit flawless data from tissues through gold electrodes. The global volume of electronic waste increases by tens of millions of tons every year. These massive mountains of waste have given rise to new industrial facilities known as urban mining. Containers filled with waste waiting at ports are, in fact, among the richest gold reserves in the world. The supply of gold in the global economy is increasingly becoming dependent on these recycling facilities. The technology behind a broken smartphone screen is transformed back into gold bullion through a chemical cycle. In the future, heavy chemicals will be replaced by solutions developed in biotechnology laboratories. Scientists are developing specially modified microorganisms to dissolve metals. These bacteria physically attach to gold flakes on the surface of electronic waste. The enzymes produced by the bacteria generate cellular energy by stripping a specific electron from the gold atom. Gold atoms with weakened physical bonds dissolve into the biological fluid in ionic form. These bacteria, multiplying in bioreactor tanks, break down massive waste without the use of acid. Heavy gold particles accumulate and cluster within the bodies of the microorganisms. As clean water is discharged from the system, only pure and concentrated gold sediment remains. In addition to biology, nanotechnology is also revolutionizing recovery systems. Synthetic polymer filters are designed to separate solutions at the atomic level. The membrane of these filters contains openings that precisely match the geometric diameter of gold ions. A mixed solution containing ions of different metals is forced through this nanometric filter under high pressure. Copper and silver ions bounce off the membrane because their physical structures are too large to pass through. However, gold ions pass smoothly through the molecular openings with perfect mechanical compatibility. On the opposite side of the filter, a liquid gold solution free of any impurities accumulates. Thanks to this technology, gold nanoparticles with near 100% purity are obtained in industrial environments. Gold atoms released from their ionic state settle back into their natural and perfect crystal structure. This element, born in the core of stars during a supernova explosion, now resides at the heart of millions of microchips. The stable gold atom formed in the depths of space preserves its physical form thanks to the laws of physics. That single atom becomes permanently integrated into the data pathways of a modern circuit board. In high-tech manufacturing facilities, pure gold layers are cut with precision lasers. Robotic arms place microscopic gold wires onto silicon layers with millimetric tolerance. The contact pins of next-generation computer processors are fully equipped with the electrical conductivity of gold. Electric current travels across gold circuits at maximum speed without encountering corrosion resistance. At the same time, high thermal conductivity prevents processors from overheating by distributing heat across the surface. This physical superiority ensures uninterrupted communication in the deep underwater sonar systems of submarines. The digital control units of high-speed trains process data flawlessly using gold components. The intense data flow in the targeting systems of fighter jets passes through gold data pathways. Quantum computers operating near absolute zero temperatures use special gold wires cooled with liquid helium. Even at the quantum level, electron flow within the gold lattice remains smooth and continuous. This unique element of the material world is a physical masterpiece of nature. From random formations inside unprocessed rocks, it transforms into a flawless and stable metallurgical geometry. Tons of worthless waste entering recycling furnaces are purified according to the fundamental laws of industrial chemistry. Each gold ingot emerging from the system is an industrial proof of the law of conservation of matter. This physical structure, based on 79 protons and its corresponding electron orbitals, becomes the most valuable key to the invisible technological world through human engineering. Every gram of gold in the electronic waste represents a perfect cycle of chemical separation and recombination. These pure ingots, stamped in modern recovery facilities, await integration into next-generation devices. The zero-emission factories of the future will continue to produce new technologies from discarded ones. Today on the Howitworks channel, we explored the extraction of gold from electronic boards and the atomic journey of matter. To continue discovering the tangible reality of engineering with us, you can subscribe to the channel and like the video.